Hello everybody, sequence series and proof day number 5, last day of this chapter. We're going to cover proof by math induction today. We're going to show the truth of a given statement or equation by using what I consider, this is my definition, but the domino effect. So what I'm going to be doing is in 3 steps, I'm going to be proving some statement, right? I'm going to call that statement P of n. And that statement is going to be some kind of equation or statement of truth, right? And I want to show truth. So what I do is in the first step, let's draw some dominoes. Okay, and we're going to call this when n equals 1. What we're trying to do is prove that P of 1 is true. Okay, now it won't always be n equals 1. It'll be our first available n. So it could be n equals 0, n equals 1, n equals 2, whatever. It'll be an integer value. We know that n will be somewhere in the integer set of numbers. So once we prove or show that n equals 1 is true, what we can do is assume that n equals true, or n is true for some value k, right? So the first domino falls. The assumption allows us to assume that P of k is true, which makes that domino fall. And if I can prove that n equals k plus 1 is true, then that allows me to make all the dominoes fall from there on out. Because if I can show that n equals 1 is true and n equals k plus 1 is true, this is a general term allowing me to show that the next term will always be true for that statement, which allows me then by math induction to show that P of n would be true for all n greater than or equal to whatever value I start with. So let's say we started with 1. Okay. So this domino effect is used in multiple ways, actually many ways. We're going to be covering a few of them in this lesson, so let's get started. Okay, so here's an example of a series. A series, as we know, is the sum of a certain number of terms, in this case a finite number of terms, where this term here is when n equals 1, then n equals 2, n equals 3, n equals 4, out to n equals n, or the nth term. Okay, we want to show that that series is equal to n squared. So we start with a statement. We're going to let P of n be the following statement. 1 plus 3 plus 5 plus 7, all the way out to the nth term, equals n squared for n greater than or equal to 1. Okay, so step one we call the basic step. And in step 1, we're showing that our statement is true for the first available n. So in this case, we want to show that P of 1 is true. So let's do that. I'm going to take the first term, which would be 2 times 1 minus 1, and show that it is equal to 1 squared. So 2 times 1 minus 1 is 1, 1 squared is 1, therefore P of 1 is true. Okay, we've knocked down the first of the dominoes. Let's go with step 2. Step 2 we call the assumptive step. And in step 2, we assume, since we've already shown it's true for one value, we assume that P of k is true. So using our statement, we can say that 1 plus 3 plus 5 plus 7 out to the kth term, which would be 2k minus 1 should be equal to k squared. So our second step is pretty basic. It's just the assumptive step that sets up the third step. So step 3 is the inductive step. In step 3, we want to prove that P of k plus 1 is true. Okay, and along in step 2 and step 3, what we want to assume is that k is in the positive integers. Okay, so let's do some work here in step 3. This is where a majority of your marks will come from, and a lot of your work obviously will be in this step as well. So I'm going to find or show that the statement is true for the k plus 1th term. So I add the first k terms, and then I add in the next, which is the k plus 1th term. And I want to show that that's true for k plus 1. So I want to show it equals k plus 1 squared. Now, just like in direct proofs, we're only going to be able to work one side at a time. So I'm going to work the left side. Always work the more complicated of the two sides. So the great thing about induction, math induction, is that step 2 will show up in step 3. So I can see step 2 is going to show up here. So I can replace this portion of my equation with k squared. Okay, so I'm going to replace this portion with the equivalent from step 2. I'm going to expand this portion of our equation to be 2k plus 2 minus 1. And in simplifying, I see that I get k squared plus 2k plus 1, which conveniently can be written as k plus 1 times k plus 1. Notice how I have not worked the right side at all. My goal is to make the left side look exactly like the right side, which will happen here in my next step, k plus 1 squared. Therefore, you must write this therefore statement at the very end. Since P of 1 is true and P of k plus 1 is true, then P of n is true for all n in Z plus by math induction. All right, there you have it. That's your first math induction problem. Let's look at another. Okay, let's write our statement to start number 2. This is another example of a series. Okay, however, it's written in a different form. You can see you have your sigma notation, but we want to show that this left side is equal to the right side for all n looks like greater than or equal to 1. Okay, so let's let P of n be the statement that the summation from I equals 0 up to the nth term of 2 to the I should be equal to 2 to the n plus 1 minus 1. So step 1, which is our basic step. Let's show that P of 1 is true. Okay, so that would be the sum from I equals 0 to 1 of 2 to the I. I want to show that's equal to 2 to the 1 plus 1 minus 1. Notice that I'm plugging in a 1 everywhere I see an n, and then we're going to do work from there. All right, so in some ways here, I am, in step 1, working both sides at the same time. So 2 to the I from I equals 0 to 1 would be 2 to the 0 plus 2 to the 1. And on the right side here, I would get 2 to the 2 minus 1. So I would get 2 to the 0, which is 1, plus 2 to the 1, which is 2, which is 3, equal to 3. Therefore, P of 1 is true. Okay, so step 1, check. Let's look at step 2. Step 2, again, is the assumptive step. So step 2, assumptive. And we're going to assume that P of K is true for K in Z plus. Okay, and the reason I say Z plus is because our first available N is N equals 1. Okay, so let's look at the assumptive steps, set up our statement there, and then move on to the inductive step. So that means that the sum from I equals 0 up to K of 2 to the I should be equal to 2 to the K plus 1 minus 1. Okay, I plugged in a K everywhere I saw an N. Let's work the third step. Okay, step 3, the inductive step. Inductive is to prove P of K plus 1 is true. Okay, again, K is in Z plus. So we're going to take the sum of from 0, I equals 0 to K plus 1 of 2 to the I, show that it's equal to 2 to the K plus 1 minus 1. Okay, let's break down real quick what the sum of the first K plus 1 terms would be. So the sum of the first K plus 1 terms of 2 to the I, from 0 to K plus 1, would be the sum of the first K terms plus then the K plus 1th term, which would be 2 to the K plus 1. So again, this right here is the sum of the first terms from 0, I equals 0 to K, and then this would be the K plus 1th term. So if I added this to this, I get that. Okay, so let's break this apart and do an analysis on it. So the sum from I equals 0 to K of 2 to the I plus 2 to the K plus 1 should come out to equal the right side. Now I have to leave the right side alone and I have to work from there. I'm going to work the left side. Well, step 2 is embedded right here. I know that the sum from I equals 0 to K of 2 to the I is equal to 2 to the K plus 1 minus 1. And I'm going to add that K plus 1th term to it. So what that gives me is 2 to the K plus 1ths minus 1. And in turn, I can add exponents, right? If I multiply two items of the same base, I add their exponents. So this would come out to be 2 to the K plus 2 minus 1, which I can rewrite as 2 to the K plus 1 minus 1. And there you have it. I've now shown equivalence to what I wanted to in order to prove that this is true by math induction. Therefore, and your therefore statement is going to be very similar most times. Okay, since P of 1 and P of K plus 1 are true, then P of N is true for all N in Z plus by math induction. I shortened math induction because I don't want to write it. You need to write it out. All right, let's do another example. Okay, so our first two examples were called series examples, just the sum of a certain number of terms trying to show that it equals some other expression. Now we're going to look at what's called a divisibility example. What I want to do is prove that 11 to the nth power minus 6 is a multiple of 5. And I'm going to do that for n in z. Okay, so it could be true for any integer. Z is the set of integers. Okay, the set of integers would be numbers like the following, and that set continued forever. Okay, I'm going to choose to let my first available n equal 1. You could choose any number, provided that it's true for that first available value. But in this case, it'll be true for all integers. All right, so let's write our statement. Let piece of n, or p of n, be the following. 11 to the n minus 6 is going to be equal to, is going to be a multiple of 5. All right, so step 1, again, our basic step. I'm going to show p of 1 is true. All right, so 11 to the first minus 6 is equal to 5 times m, where m is in the integers. So this is the definition of multiple of 5. 5 times some integer value. So let's show that this is true and that m is an integer. So 11 to the first is 11, minus 6 is 5. Therefore, in this case, m would equal 1. Thus, p of 1 is true. Okay, I've shown it's true for step 1. Let's assume it's true in step 2. Okay, it's our assumptive step. Okay, and our assumptive step is to assume p of k is true. You're starting to get the swing of things here. We're going to put k in the integer set. Therefore, 11 to the k minus 6 should be equal to 5w, where both k and w are in the integers. Okay, now I have to use w because I don't necessarily have the ability to assume that it'll be the same value as m above. Okay, let's move to step 3. Step 3, of course, is the inductive step, where we will prove p of k plus 1 is true. All right, let's do a little work here, leaving step 2 within our window so we can see when to use it. Okay, so I've got 11 to the k plus 1 minus 6 should be equal to 5q. Now I'm going to write that we're going to use q because, of course, we can't use w or m like we did before. Okay, so let's break this up a little bit. What would a to the x plus 2 be equivalent to? Well, that would be a to the x times a to the 2. So I'm going to break 11 to the k plus 1 up into 11 to the first times 11 to the k. Now, I'm going to do that, and the reason I'm going to do that is because eventually I want to see step 2 showing up. Okay, so what I can do then is if I have 11, let's say a to the x's, that would be equivalent to 10 a to the x's plus a to the x, or 1a to the x. So I'm going to write this as 10 11 to the k's plus 1 11 to the k power minus 6. And you can see now that step 2 is going to show up right here. All right, so we get 5w. We can assume that 11 to the k minus 6 is equal to 5w. And of course, 10 is a multiple of 5, excuse me. So I could pull out a 5 and leave 10 times 11 to the k is 5 times 2 times 11 to the k. Now I can pull a 5 out of both of those terms. So I would get 2 times 11 to the k plus w. Now since k and w are both in the set of integers as defined above, then 2 times 11 to the k plus w will also be in the set of integers as listed above. Thus, 2 times 11 to the k plus w will have to be equal to q. Okay, let's look at why. 5 times some integer is going to equal 5 times an integer. Therefore, we could say that 2 times 11 to the k plus w is equal to q. All right, therefore, since, now we start our therefore statement, p of 1 and p of k plus 1 are true, then p of n is true for all n in Z by math induction. All right, there you have it. We got a couple more examples, unique one coming next and on the last page. Okay, example number 4 is considered a product example. You can see that I've got the product of n number of terms, and it looks like my product starts here where n equals 1. So I'm going to let p of n be this stuff. Okay, I'm not going to write it all out, but I'm going to let p of n equals that, where n is in z plus, right? So it starts with 1 and goes up to the highest integer you can think of and more. Okay, so I'm not going to write all that out, but let's do step 1 through step 3. Step 1, again, basic. I'm going to show p of 1 is true. All right, so p of 1 is going to be 1 times 1 factorial, and that should be equal to 1 factorial to the 1 plus 1th power, right? So I took the first term over here and plugged in a 1 for n over here. Okay, let's show truth here. So 1 times 1 factorial is 1 times 1, which is 1, and 1 factorial is 1 to the 2nd power, which is also 1. Therefore, p of 1 is true. All right, step 2. Our assumptive step, we're going to assume p of k is true, where k is in z plus, right? All right, so that would mean that 1 times 1 factorial times 2 to the 2nd times 2 factorial times 3 to the 3rd times 3 factorial multiplied all the way to the kth term, which would be k to the kth power times k factorial, should be equal to k factorial to the power of k plus 1. All right, there's step 2. Let's do some work now in the inductive step, step 3. Let's prove p of k plus 1 is true. All right, let's dig into this a little bit. All right, so if p of k plus 1 is true, then that would mean 1 times 1 factorial, 2 squared times 2 factorial, 3 cubed times 3 factorial, k to the kth times k factorial, and then we put in the k plus 1th term, k plus 1 to the k plus 1th times k plus 1 factorial should be equal to k plus 1 factorial to the k plus 1 plus 1th power. Okay, this is awesome. Love it. Maybe you don't so much, but that's okay. All right, here is step 2. Step 2, I can replace with k factorial k plus 1th power. All right, now I'm going to multiply that by the k plus 1th term. All right, so let me put that right here, k plus 1 to the k plus 1th times k plus 1 factorial. Now my goal is to show equality or equivalence to what we've got on the right side there. So I've got some work to do. Okay, so what I first want to do here is I'm going to take this k plus 1 to the k plus 1th power and k factorial to the k plus 1th power, right? So if I had a to the 3rd times b to the 3rd, I could write that as a times b to the 3rd, right? So I'm going to pull the k plus 1 times k factorial and put that all to that power, k plus 1th power. All right, and I'm just going to drag this piece along with, which is k plus 1 factorial, just for a moment. Okay, now by definition, k plus 1 times k factorial is actually k plus 1 factorial. And I'm going to take that to the k plus 1th power. Okay, so if I had x to the k plus 1 times x, I could write this as x to the k plus 1 plus 1. All right, I'd add their exponents. In this case, we can rewrite them, since I have k plus 1 factorial to the k plus 1th and k plus 1 factorial. I can write this as k plus 1 factorial to the k plus 1, which is right here, plus 1, which is right there. Okay, which, hey, go look at that. I get exactly what I wanted, k plus 1 factorial to the k plus 1 plus 1th. Therefore, statement, since p of 1 and p of k plus 1 are true, then p of n is true for n in z plus by math induction. All right, guys, we got one more example. Okay, you can consider this derivative example, at least at this point in our course, to be a challenger. However, by the end of the course, this is a potential exam question. So I want you to feel somewhat comfortable with this eventually. So at first, it's not going to feel great, but we'll get there. Okay, so given that f of x equals 1 over x, for all integers n greater than or equal to 0, its nth derivative is given by the following. So this statement here, or this equation here, is one that represents the nth derivative. So the 0th derivative would just be the function itself. Okay, so I'm going to let p of n be that statement above. For n in z and n greater than or equal to 0. Okay, so it's an integer greater than or equal to 0. It's not just the positive integers, but also starts at n equals 0. So step 1. Our first available n is actually to show that p of 0 is true, but I'm also going to show that p of 1 is true. All right, and because the 0th derivative isn't actually yet a derivative for this function. So p of 0, what would p of 0 equal? Well, that would be the 0th derivative of f of x, which would be negative 1 to the 0 power times 0 factorial times x to the negative 0 plus 1th power. So the function, which is the 0th derivative, would be negative 1 to the 0, which is 1. 0 factorial is actually also 1, so keep that in mind. And then x to the, what would be negative 1st. So that's telling me that f of x is 1 over x, which it is. So it's true, therefore p of 0 is true. Let's show that p of 1 is true. So the first derivative of f of x would then be negative 1 to the 1st times 1 factorial. Let me get rid of this over here, times x to the negative 1 plus 1th power. Well, what that comes out to be is a negative x to the negative 2nd, which is negative 1 over x squared, which actually also is the first derivative for 1 over x. So p of 1 is also true. Okay, step 2, of course, the assumptive step. Let's assume, assume p of k is true. And of course, let's put that for k in the integers. Oops, I didn't want positive integers, such that k is greater than or equal to 0. Okay, so that would mean then that the kth derivative of 1 over x would be negative 1 to the k factorial, x to the negative k plus 1. Step 3. My writing's getting a little sloppy here. I'll slow it down. The inductive step. Let's prove p of k plus 1 is also true. Okay, so this is a unique example, and I'll show you why in just a second here. But what I want to do is show that the k plus 1th derivative of f of x would be equal to negative 1 to the k plus 1. Well, I hit some button. I don't know what I hit there. Okay, let me scratch that. There we go. Okay, negative 1 to the k plus 1 times k plus 1 factorial times x to the negative k plus 1 plus 1. All right, so how we do this when you get a derivative example is to get the k plus 1th derivative, all right, in this form, you have to take the derivative with respect to x of the kth derivative of f of x. Okay, so by definition of the derivative of the kth derivative is the k plus 1th derivative. I know it's kind of odd and a little bit crazy, but what I'm going to do is I'm just going to take some derivatives, and anything that isn't an x is treated as a constant. So I'm taking the derivative of the statement from above. Now I'm using step 2, and I'm inserting it right here. So anything where you see a k is going to be a constant. X is the only variable in that expression. So negative 1 to the kth is a constant. K factorial, a constant. I have x to some power. So all I'm using is the power rule. So the k plus 1th derivative is equal to the derivative of the following. Well, all that would be is negative k plus 1. I bring the power down in front. Negative 1 to the k plus 1. Oops, excuse me. Got ahead of myself. K factorial. X to the negative k plus 1. With the power rule, we always take away 1 from the power. Okay, so the k plus 1th derivative. Check out how slick this is. The k plus 1 times k factorial gives me k plus 1 factorial. That's awesome because I see that that's what I'm trying to prove above. You can see I want k plus 1 factorial. Okay, let's continue. This negative 1 here times a negative 1 to the kth power will give me -1 to the k plus 1. And x to the negative k plus 1 minus 1, if I pull a negative out of both of these terms here and here, that would be a -1 times k plus 1 plus 1. And there you have it. I now have this in a form, if I nest the parentheses here, that matches step 3 exactly. So I used step 2 to go from here to there. All right, therefore, since p of 0, p of 1, and p of k plus 1 are true, then p of n is true for all n in z plus by, I'll write it all the way out, mathematical induction. All right, guys, it's math induction. We'll get plenty of practice in on this, and we'll actually see it again later on in the year. So, hope this was good. Have a great day. See you in the next video.